group conversation, get back into where, if you're coming back to your place from going for a walk, which would be a good idea, it's kind of settling yourself again, finding the good position, a little bit of attention to your breath again, to your where your feet are placed, where how your spine is aligned. Just getting ready for this last hour of work. All right. Coming back. We're going to have our three talks today by David Theurel. Well, first talk by David, then Fred Cooper is going to give us a practice actually, which will help to keep making sure that we have both sides of this kind of conceptual and non-conceptual. His practice is actually on non-conceptual nature of mind, which I think will be helpful going forward, and then finishing up with Eric. So we'll try to keep these reasonably on time with a few questions after each, and then wrap up around 1:45, 1:50 with some final comments to get ready for tomorrow. So on that, David, you can take it away.
Thank you.
If you want, each one of you can give a brief introduction of yourself, however you think is most relevant to introduce yourself.
Let me just try to share.
Are we recording?
I got it covered. Thanks, Stevie.
Thank you.
Does this work? Does this look like, can you see my slide and not my notes?
We see both right now.
Yeah, I think we're in your presenter view, so if you can be a little bit easier if you switch it to the public view. So we're seeing what should be on your laptop screen, I think, with notes and everything.
Okay.
It still
5 years
works
after,
if, yeah.
so long after the pandemic, and I still haven't figured this out.
Yeah, so I think that still works.
Is it in Zoom when I share, instead of sharing the desktop, I should share the app? Is that what I should change?
Yeah, you could try that.
Unfortunately, I can't find the.
No, it's still
Right.
everything. It's okay. Maybe if you just make the slide a little bigger, and then the
Okay.
notes will be more.
Yeah, we can follow along with the notes as well. Ah, there we go. That I think is it. There, perfect.
Wonderful. Okay. Name is David Theurel. My background is, I might have mentioned this before, I come from physics, and the last maybe 7 or so years I've been working a little bit in neuroscience, but really I feel more comfortable in physics. And anyways, trying to bridge that gap. The work that I want to tell you about now is much more on the physics side of things, but hopefully it has some connections to the topic of this conference. So I titled it, What Classical Physics Has to Say About the Structure of First-Person Experience. So going by that title, hopefully it will have some connections. Okay, this is a new way of presenting the topic for me, so please bear with me. Okay, let me start by drawing your attention to this figure on the right. This is Wheeler's, from famous great physicist John Wheeler's U, which I think he used, my understanding is he used to illustrate an idea of his of, I think he called it the participatory universe. And this, I think he had this slogan, bit from bit. I think he was advocating the view that information is somehow fundamental and then matter somehow emerged from it. And so I'm using this figure a little bit. It's a little bit ironic because I'm taking entirely the opposite perspective. Although I like the figure, but I want to illustrate. I want to take the other approach, bit from it, which I think is much more, pedestrian, flat-footed. The typical thing in materialist reductionist view that we often take in science, which is the world is made out of matter governed by some dynamics, by some laws, and things like agents and information and probabilities are emergent. So this is the view that I want to take. And let me set it up like this. Scientific theories adopt what we might call the view from nowhere, using language from Thomas Nagel, which is that they describe the world objectively or detached from any particular viewpoint. And physics is the utmost example of this, in which we describe the world as consisting of these abstract, even mathematical, very mathematical material objects, be they particles, fields, or quantum states, and then evolving under some mathematical dynamical laws. There's no it's an uncentered view, an ontology without a center, without a subjective viewpoint. And of course, there's this very profound question of how might subjective first-person experience emerge from such an ontology? Is the hard problem of consciousness. I'm utterly puzzled by this question, and I'm not going to try to contribute anything to that here. My mind has already been blown more than one time during this conference on this very topic. But the topic that I want to talk about is this other one here, which is actually much more tractable, which is what must be the structure or the structural features of that first-person experience, taking for granted that it exists. And the approach that I advocate, as I said, is very flat-footed, which is this, I've been calling it bit from it approach. It's nothing new. It's just the idea that the structure of first-person experience, say the theory of measurements or the epistemology or theory of knowledge, in a given ontology or a given theory of physics, may be deduced by treating the observer or the subject as just another object or material physical object, and then modeling observations and measurements as ordinary physical interactions between objects, right? It's the least surprising approach that you might take from a reductionist approach to science. So here's the problem that I would like to solve. On the right, you have some system, it's called the object system, S, and then on the left, there's some observer, and I want to, the observer is going to try to interact with the system or is trying to observe it, extract information from it. And I want to ask, what are the possible measurements in a given theory of physics? So if you give me quantum mechanics, or if you give me Hamiltonian mechanics, classical Hamiltonian mechanics or Newtonian mechanics, what are the possible things that can be observed or measured? What things cannot be observed or not measured? Maybe counterintuitive in classical physics, but I've found that it's gone largely unexamined, that it's just been assumed that we have direct epistemic access to things, and that hasn't been studied with sufficient rigor. And also questions of what can you given two observables A and B, can you always observe A and B, or can you observe A without disturbing B? These kinds of questions. And the strategy, what I'm calling bit from it, is that of course you can just treat the observer as another object, treat the observation as some physical interaction, describe the whole joint system by the laws that you have specified for your physics, and from there you can deduce the answer to the question. You very often modeling a whole observer, like a whole person, is except in special cases, and I'll give an example where it is possible to do, but usually it's out of the question. But you can then use this stand-in, this I'm calling it a once removed approach, where instead of modeling the observer inside of your system, you have some intermediate system called the measuring apparatus, which it is going to be coupled to the object system. They're going to interact, you study that. And then you make some assumptions about how the observer can extract information from the measuring apparatus. This is all very high level. I'm not going to use, maybe I have 1 or 2 equations down in the slide up ahead, but very high level. And there's lots of things that we could get into in every part of this, especially this blue arrow about observation. There's some delicate stuff.
We're about halfway through on time, by the way.
Oh my gosh. Okay, let me just give you some examples. Yeah, there's this wonderful example in the history of physics of applying this approach. So this is Galileo's ship experiment, 1630s. Galileo was an advocate of the Copernican model of the solar system. He believed that the Earth was in motion, both around the sun and also around its own, spinning around its axis, as opposed to the Ptolemaic model, where the Earth was the center of the solar system. And he received a lot of pushback. The Inquisition, the Holy Inquisition, didn't appreciate his views, and he defended them by, he wrote this thought experiment about, imagine you're in this ship. Let me just read it. He says, shut yourself up with some friend in the main cabin below decks on some large ship, and have with you there some flies, some butterflies, and other small flying animals. Have a large bowl of water with some fish in it. Hang up a bottle that empties drop by drop into a wide vessel beneath it. With the ship standing still, observe carefully, ... He goes on to describe several things that you can observe about these systems that he's introduced. And then he says, then have the ship proceed with any speed you like, so long as the motion is uniform and not fluctuating this way or that. You will discover that not the least change in all the effects named, nor could you tell from any of them whether the ship was moving or standing still. So here, Galileo is arguing, I should have said this earlier, the main counter argument to the idea that the Earth is in motion, at that time, it was very intuitive that you could tell if you were in motion. It would be very obvious if the Earth were flying through space at thousands of kilometers per hour. If you were to throw a rock one way, it would fly differently than if you were to throw the rock the other way. If you were to jump one way versus jump the other, smoke would rise and go a certain way instead of straight up, these things. And with this thought experiment, Galileo at this point didn't have Newtonian mechanics, but he proposed that, he intuited that all of these experiments would come out exactly the same if the ship was stationary versus in motion. So he concluded from here that there's a certain observable of the system. In this case, the system is, in his example, would be the ship or whatever vessel you're in. The observable that he's interested in is whether you can measure the absolute state of motion of the ship. And he's introduced this intermediary, which I'm calling M, which are all these, the flying insects or the drops, falling drops of water or what have you, the smoke. And by observing, he had some intuition for how these would interact, and then he inferred that, in fact, you cannot observe. There is a thing that you cannot observe, which is the absolute state of motion. The Inquisition didn't like his argument very much. They weren't convinced. They put him to trial, found him guilty of suspicion of heresy. He was forced to recant, and I think he spent the rest of his life under house arrest. I don't know if it's just if it actually happened or if it's just a story, but they say that he rebuked when he was sentenced that, and yet it moves, right? He was stubborn. Just a small anecdote. A week ago, a friend of mine was at the Museum of Galileo in Florence, and he sent me his picture of this preserved middle finger of Galileo, which I found very funny. Like maybe he was getting back for this judgment. Anyways, this I'm presenting it as this example of applying this technique. Let me go to an example number 2, jumping forward 50 years into the future. Now, Newton had published, oh my gosh, had published his Principia. Okay, I'm at peace with not getting to the point of my own work, but I'm just kind of sharing this this framework. Right. Once you have Newton's laws, because they're second order ordinary differential equations, you can very easily show no matter how complex the agent is, and a whole human, whatever you might have, as long as it's governed by Newton laws and some minimal structure, you can show that no matter what inertial frame of reference you choose, the equations stay the same. So you can infer that there's no way that you could measure that observable. Let me give another example. Now jumping forward to the 1940s, textbook quantum theory. So this talk isn't exclusively about classical physics. In quantum theory, as you study, usually there's these two rules: unitary dynamics and projective measurements. Now, if you want to study the things that you can observe about a system in quantum theory, instead of applying the projective measurement directly, people have taken this once removed approach where you first couple the system to an apparatus using a unitary evolution, and then you do a projective measurement on the apparatus. And this results in the general theory of measurement, or positive operator value measures. You can study continuous measurements, inefficient measurements, joint measurements of multiple observables, a bunch of really cool things. And I guess I'm just trying to convey how this approach is very fruitful to studying the structure of this kind of deep question of first-person experience, of the things that you can come to know about the world. I'm probably out of time. Let me just couple of words about what where this direction has taken me, or where I've taken it. I've been studying in the context of Hamiltonian mechanics, classical Hamiltonian mechanics, when you have a system that you want to observe, and you do this, you take this technique, you introduce a measuring apparatus, couple them, you study the Hamiltonian dynamics of the two joint systems evolving, and then you extract information from the measuring apparatus. I found that this, when I did a literature review, surprisingly has not been done with any care in Hamiltonian mechanics. You would think that at this point it had been worked out, but everybody just takes for granted that you can measure without disturbing. And so these are two of my papers. I've been working on this for about 5 years at this point. I had my first paper on it last year. It's in PRE. I invite you to check it out if you're interested in more of the details. The key finding is that the theory of measurement, or even you might talk about the epistemology of Hamiltonian mechanics, is non-trivial, and it's surprisingly reminiscent of the structure of quantum measurement. There's incompatible observables, and there's an algebra of observables instead of the commutator of observables. You look at the Poisson bracket, and if the two observables don't have zero Poisson bracket, it turns out that you cannot measure the one without disturbing the other, and this places limits on how much you can ever come to know about two observables. All right, I'll stop there. Thank you.
All right, thank you, David. So I think, yeah, to keep things on time, I think we should try to just keep plowing along to the next topic.